Hi everyone, my name is Steve. Today we're going to go through depth-first search. This is a very classic and useful graph search algorithm. I'm sure you'll encounter them in many of your interviews. And if you deeply understand this problem, you can immediately tell from the surface of the interview problem whether depth-first search is a good candidate for the algorithm that you should pick. So we'll go through the basics today. So first, as its name implies, we search as deep in the graph as possible. And when depth-first search explores edges out of the most recently discovered vertex, we'll call it V, that has unexplored edges leaving it. And as soon as all these edges have been discovered, and we'll backtrack to explore edges leaving the vertex from which V was discovered initially. So we'll backtrack. This process will continue until we have discovered all of the vertices that are reachable from the original source vertex. And if any undiscovered vertices remain, then depth-first search will select one of them as a new source, and it will repeat this search from that source. This means we'll produce a depth-first forest instead of a tree. We'll go through that in just a second. And the algorithm repeats this entire process until it has discovered every vertex in this graph. That's the theory of this depth-first search in plain text version. Next step, we'll go through what that really means. We'll use a graph to illustrate this first, and then we'll use a real code instead of pseudocode. Similar to last time for when we talked about breadth-first search, if you missed that, I'll put a link here just to click that. We'll still use three colors to represent different states. We'll use white to represent the very initial state. What that means is that we'll color every vertex to white and in the very beginning, just to indicate that this is a brand new vertex that we haven't visited yet. And the second color is gray, which means we have discovered this vertex. We are exploring all of the adjacent vertices that is connected to this vertex. That's what gray means. And black just means we have completely finished. We have exhausted all of the adjacent nodes that are connected to this node. And then we'll mark it as black. We'll use two timestamps. This is something new that we didn't use in breadth-first search. First one is UD. D stands for when it's discovered. And UF. F stands for when we have finished traversing all of its adjacent vertices. The lower and upper boundary of these timestamps will be all integers. We'll just assume they are all integers. And the boundary of this will be between 1 and twice of the number of vertices. So if, say, there are 4 vertices, the upper bound is going to be 8. We'll see that in just a second. And vertex U is white before U.D. That means before it's discovered, we mark it gray. It will be white before we mark it as gray. And gray will just means the timestamp is between its discovery time and its finish time. And black will be after U.F. That's what it means. All right. Suppose we are given such a graph, A, B, C, D, E, F. It is alphabetically horizontally sorted, just for easy reference. Back to the idea of depth-first search, we're just to pick one node. You can pick any node. In this case, we're just going to pick A, since that's the beginning of the alphabet. You can pick any one that you want. But if you pick a different one, the forest that you're going to form is going to be different. Initially, every single node is white. That's the beginning state. We'll color every single vertex to be white. And then after this, when we discover a node, we'll color it to be gray. We'll start from A, so we'll color A to be gray. And this one, right now, all of these 5 nodes, they don't have any discovered or finished timestamp. But for this one, we'll start with timestamp 1. These timestamps are integers. We'll just simplify that. Beginning from 1 up to 2 times number of vertices. So there are 6 vertices here. So the max bound for the timestamp is going to be 12. The last timestamp that we're going to use to discover the last vertex is going to be 12. That's going to be the finished timestamp of one node in this graph. For this, what I'm going to use is the first integer is the discovered timestamp. The number that comes after that slash is the finished timestamp. That's what the number and the color indicate. We start from A, color it to be gray. So we have discovered this A. Next, we're going to discover what? All of the adjacent vertices that are connected to A. Next one is B. So we discovered B. It took us one more time unit. So B's discovered time is 2. Then we'll continue to explore. As the definition of depth-first search says, we'll continue to explore as deep in the graph as possible. From B, we're not backtracking to A because we have something else we'll continue to discover. Next one is E. It takes us one more time unit. So the discovered time of E is 3. And then we'll continue to go even deeper, right? We're not backtracking yet. Continue to go even deeper. That is D. We discovered D. It took us one more time unit, so D's discovered time is 4. Right now, all of these have been discovered, and all of them have been marked gray. Is there anything that is adjacent to this node with D that hasn't been explored yet? Is there any? None. At this moment, we have explored to the deepest level of this possible route. That means we have traversed all of the adjacent nodes. So we'll start backtracking. So we'll mark this one to be black. That means we have visited all of its nodes. And we put 5 here because 5 is the finished timestamp of this node. Now we'll continue to backtrack. Next time is 6. It took us one more unit, so it's 6. We backtrack to here. This is the path that we started from A, go this way, this way, this way. Now we started to backtrack here to here, right? So now it's 6. It's going to take us one more time unit. So it's next time it's 7. So 7 is the finish time for B. Continue to backtrack. That is 8. 8 is the finish time of the node A, of the vertex A. I'm using node and vertex interchangeably in this context. So we have built this depth first tree, but we haven't finished traversing this entire graph. If you recall the definition of depth first search, we'll continue to go through the graph. We'll just pick another node as the starting node, as the source, and continue to repeat this process until we have traversed all of the nodes. So next, we'll pick this one. We discovered C, so we mark it as gray. Next time is, so beginning from 8, next one is 9. So the discovered time of C is 9. And then C goes to, we'll only discover the undiscovered, which means it's white. The color is white. So see this one, it's also directing to E, but E is black, which means we have completely visited it. Even if it's gray, we don't go there. We only visit the white nodes, right? Which means we have never touched. Next one is F. Discovered time is 10. Then there's nothing more to go. So we'll just go back. We finished traversing. So we add a finish timestamp to F. That is 11. We'll continue to backtrack. At this time, we'll continue to backtrack. Now it is 12. Now we have finished traversing through all of the vertices in this given graph. Now let's take a look at the start time and end time. The start time is 1. The very start time of this entire graph, and the finish time is 12. 12 is twice of the number of the vertices, which is 6, which meets this definition. It's between 1 and twice of the number of edges. Again, you see here, we produced a depth first forest. In this graph, there are 2 depth first trees, one tree, another tree, right? So this graph, after traversing through this entire graph using depth first search approach, we have produced a depth first forest. In the purpose of this demo, we started from 2 nodes. One is A, the other is C, and we use exactly the same process. We'll continue to explore as deep as possible. Now let's think about the time complexity. Suppose the number of edges is E, and the number of vertices is the variable V. What will be the time complexity using these 2 variables? The big O notation, V plus E. It's linear to the number of vertices plus number of edges. If this is not clear, we'll go through the real code walkthrough right now. Then you'll completely understand the time complexity and how depth first search really works. Now let's go there.